Right on. Okay, so welcome everybody to our 10th episode of this SFU Sports Analytics virtual seminar series. It's my great pleasure to have Dr. Alexander Leblanc and Robyn Ritchie from the University of Manitoba to speak to us today about scoring rate estimation in European soccer. Dr. Leblanc is an associate professor in the Department of Statistics at the University of Manitoba. His research expertise is in non-parametric statistics, data depth and function estimation in particular, and computational statistics, although he has traditionally been more involved in the theoretical and theorem-proving type of work. This focus has evolved over the past few years, and he is thrilled with the latest developments with respect to sports analytics. Sports data was in fact the reason he became interested in statistics entering university, in particular baseball and his beloved Expos in Montreal, although he only recently started to get more seriously involved with sports analytics as a research pursuit. Robyn Ritchie has completed her undergraduate degree in statistics at the University of Manitoba and is now a second-year master's student under the supervision of Dr. Leblanc. She loves sports and plans to continue onto PhD studies in which she hopes to revolutionize the game of curling with sports analytics. And certainly with the push with the CRT and whatnot, hopefully you can get you involved in the high-performance sports in Canada, and I'm sure curling would love to have you aboard. All right, so in terms of the topic, they will discuss the modeling of game outcomes based on Poisson processes and briefly consider a few questions that can be answered with such models. Based on generalizing the simple independent Poisson model, we also look at semi-parametric estimation of time-varying scoring rates, league-wide and team-specific, and consider questions related to team performance. Specifically, we compare scoring patterns between home and away teams and between teams entering the period of extra time, leading, trailing by a goal. We will also address issues surrounding data collection. So with that, I will stop sharing my screen and turn it over to Dr. Leblanc.
Okay. Oops. I think we're both pushing the buttons at the same time. Okay.
There you go.
So thank you very much for the invitation, Dave. It's a pleasure for me to be here. I do want to, so let me start just very briefly by saying that this work started, I guess, officially about 2 years ago now, a little bit more, with Robyn, she was an undergrad student and did a USRA project where we started to collect data and look into these things. And at first it wasn't clear what would come out of it, but it's been a pleasure working with Robyn. And it's really interesting, the stuff that we were able to put together. So hopefully you guys will enjoy it. So whenever I give a talk to a different kind of audience, different from like a regular stat department, I always have the problem that I tend to be of the mathematical type of guy, and so my talks tend to I tend to present in a style that will not be the greatest for everybody, but I'll do my best, and don't hesitate. Let me know if you feel this is too technical. I think I got rid of most of the technical stuff that's less interesting, and my goal is really to give you a good idea of what's going on and the things we can do and where we want to go with our work. Okay, so so the talk is going to go like this. We're going to briefly talk about the independent Poisson model, which is the basic one that you may have seen. If you've looked into any kind of outcome modeling for games, you would have seen something that looks like this somewhere. And I'm going to talk about a couple issues with this model and lead to where we want to go next and where the idea came about as to using semi-parametric estimation here. And then I'm going to pass it over to Robyn, who's going to talk about the data that she collected and how she actually constructed these non-parametric estimators for scoring patterns. And then she's going to show you a couple of nice graphs that are actually what this is all about, trying to make sense of what's going on during the game. So are you guys seeing me change my my slides?
You're still on the title page.
Yeah.
Ah, okay. So it says, I see now, oh, I pushed the wrong button. I'm actually now on the introduction. I actually went through the outline of the presentation. So sorry about that. That was my mistake. I should have seen this coming. Yeah, so 5 parts, I guess, to the talk, and Robyn's going to take care of the last 3. Okay. So quite a bit of work has been done on modeling outcomes for soccer games. There's really, and many other sports. Generally speaking, there are 2 main categories of models that people will use. Those direct models tend to focus on modeling the outcome of the game directly. So you're looking at modeling the probability of a win, let's say in soccer, a win, a tie, a win for the home team or the away team, and then a tie. So it's kind of like, look, that would be logistic regression, but really multinomial regression, because there would be 3 outcomes here that we would like to model. So that's one way to go, obviously. However, a very popular approach is to use an indirect modeling approach, which would focus on modeling, goals scored if you're thinking of soccer, but if you're thinking of another game like points in general in football or anything else, trying to model the points that are going to be scored by both teams. And of course, if you can model points or goals, you can also model outcomes indirectly. So that's why they call those indirect models. Now, these models have their different focus, and so they allow us to understand or look at different things when you fit them. So now, why modeling outcomes? Obviously, there's all the hype around fans of the game who like to do these kinds of things, to just play around and make sense of what's going on. But more than that, I guess, it allows to understand certain elements of the game, like home advantage, if you would like to quantify that, or red cards, for instance. So I did some work on this before a few years ago that I presented at the SFU. You can also look into like team fatigue and different things, and impact of traveling on games. Another interesting thing that people like to do is ranking teams, like coming up with some kind of a power index or something for teams. So if you want to do something like this, trying to quantify like which team is really the strongest. Obviously, game outcomes will tell us something about which team is the strongest, but that's not all of it we know. A team that plays in a tough, division, for instance, may be stronger than its record will suggest. And this is another thing that's really important in certain leagues, for instance, in college sports in the US, where they really want to have these national rankings, but certain teams never play each other. So how do you manage to actually compare them? Well, you have to have some kind of model to be able to say something about what might be happening truly. Any of the professional sports, not any, but most of them, NFL, NHL, and so on, the schedules for the teams are not balanced. And so that's another thing where you want to use a model to be able to understand what's actually going on. That's not so much an issue at the end of a season for most, like the European leagues, where the schedules are perfectly balanced. So all the teams play each other exactly the same number of times. So that's less of an issue, but it's definitely an issue along the way. If you want to do this kind of analysis throughout the season, then teams have not played each other sometimes midway through the season, right? Now, obviously, the betting industry is another important user of modeling, modeling models like this. But I myself, I stay away from that part. That's not the part that I'm really interested in. Okay, so I guess, so these models are simple, or you want to have them as simple as possible to make sense of what's going on. But they are, of course, they do have some shortfalls. It's a little bit difficult to understand or sometimes impossible to understand the impact or worth of very specific, less typically dramatic actions during a game, like was a pass a good pass or not. Those kinds of things are hard to understand and quantify, but the kind of model for outcomes of a game that I'm going to talk about today, they don't allow this, right? They don't go into the game enough to be able to say anything about these kinds of specific actions. Same things, if you want to know which type of actions will increase the chance of scoring or winning the game, you won't be able to do something like this. You would need, more data, better data, and fancier models to be able to do this. Even looking at game strategies, hard to incorporate in such a model. Interesting to think of, but hard to do. And player evaluation is a little bit tricky, obviously, is a difficult thing to do. But with these kinds of models, it doesn't naturally come out. So I guess more and more now you've got these expected goal or expected value type metrics that people are working on. And that's where you would want to go if you want to quantify these kinds of actions or or get into player evaluation, these types of models will do it for you. But the price to pay is these models are a lot more technical and a lot more difficult to fit, obviously, and to understand. Okay, so the simplest model is probably this one here. So that's the independent Poisson model. So there's this paper by Lee in 1997 in Chance, which is not very technical. It's just essentially saying, assume that X is the number of goals scored by the home team, and Y is the number of goals scored by the away team, and assume that these two are Poisson distributed with theta, each their respective scoring rate, or this theta sub H here is the expected number of goals for the home team for that game, and theta sub A will be the expected number of goals for the away team for that game. And so the subscripts I and J, what they have to do is specifically they are team identifiers. So when the home team is team I and when the away team is team J. And then they assume also independence between the goals scored by both teams. Obviously, this is not a realistic assumption. It's very clear that the number of goals scored will be affected by what's going on throughout the game and by what the other team does. But it turns out that the reason people are still using this model is because it actually does a surprisingly good job at modeling outcomes for games. So what you further do is then this theta sub H, what you do is you use a log link for it, and you write the log of theta as this mu plus delta plus alpha I plus beta j, and then the log of theta A you write as mu plus alpha j plus beta I, kind of like a ANOVA model really is what you're doing. But it's in a GLM framework, right? And so here the mu is this overall league scoring effect. The delta is the home advantage in this case. So you can see it's only included for the home team. Alpha I is the offense for team I, so that's the offense for the home team, and beta j is the defense for the away team and for theta H. And then for theta A, you just flip them around. Alpha j is the offense for the away team, and beta I is the defense for the home team. And so when you do this, you have to impose this constraint. The sum of the alphas and the sum of the betas has to be 0. Again, that's the spirit of ANOVA. If you don't have these constraints, then your model is not identifiable. So that's the math side of it, I guess. The interesting side of it is when you have this constraint, it makes the alphas and the betas really about relative strength of these teams. So if an alpha is greater for a team than for another, that implies that they have a better offense, really. But it's not directly related to how many goals they're going to score. Now, alpha and beta being 0 for a team, that would imply that you have a completely average team both on offense and defense. So what you do, of course, is you collect data like this here for the 2016-2017 season, and you have to have all the outcomes of all the games. Once you have that, you can just go ahead and fit the model and estimate all the parameters for all the teams, right? So, so for instance, if you use this data from 2016-2017, so that was the year where Chelsea won 30 games. That was the first time a team ever won that many games. Of course, that record has been beaten 3 times already since then. But that was the first year this happened. And so when you fit the model, you get these estimates. Mu hat is 0.08 or whatever. Delta hat is 0.28. That's a little bit more interesting. That says that the home advantage here translates into a 33% increase in scoring. So that makes the expected number of goals for the home team 33% large, 33% larger than the one for the away team. But so what that also implies is if you have 2 average teams playing, so that their alphas and betas are all 0, this is the situation down here. So you get the expected number of goals for the home team is 1.45. The expected number of goals for the away team would be 1.09. And then you get the probability for the home win, the tie, and the away win here. And you can see the home team is favored in this case. So that would be for 2 average teams playing each other. Now, when you fit the whole model, of course, you get these parameters for all the teams. You get the alphas in red there on my graph. You see the alphas for all the teams going on the left from Chelsea, Tottenham, and then Manchester City, Liverpool. And so the teams here have been ordered in terms of their rank at the end of the season. And you can see in red, you get all the alphas. In blue, you get the betas, which are the defense parameters. And so you can see that here, Tottenham is the one with the best defense. Manchester United had the second best defense in blue, and then Chelsea as the third best defense. And if you flip it around and look at offense, actually Tottenham also had the best offense. And then Chelsea had the second best offense according to these parameters. So if you want to rank the teams here, what you would do is you would go alpha minus beta. So a large alpha means a very good offense, and a negatively large beta means a really good defense. So when you go alpha minus beta, what you get is, if that is large, that implies you have both a very good offense and a very good defense, right? And so when you do this, you can see that, of course, you go back, and if you look at the standings, these parameters or these measures of how good a team is, it more or less follows the table, except for, in this case, here. So you can see that Tottenham is apparently stronger than Chelsea, according to how this model fitting here. Now, this is something that's easily understood when you go back and have a quick look at the standings. It has to do with the goal difference here. So the problem with the Poisson model, I guess, is that it tends to overemphasize goal differences. It's fully based on goals, and it's not really using wins and ties and losses to do the model fitting. And so that's a common thing. It looks like Tottenham is the best team here. And, well, that's what comes out when you fit the model, right? That's not that surprising. Okay, so if you actually want to do anything like for a specific team, then you can use, like here, the alpha for Chelsea and the beta for Chelsea. And then you can calculate probabilities, chances of Chelsea winning if they're playing an average team at home, or the chances of Chelsea winning if they're playing an average team but they're away. And you can see there's quite a bit of a difference. The probability for winning home and away is different, and it accounts for the fact that they do have or they don't have the home advantage, for instance, right? Okay. So now, the one interesting thing that this kind of model does allow is you can do all kinds of interesting simulation studies to try and get after questions that might not be easy to get to otherwise. And so here's a simple example of something like this that can be done. So if you look at the data that year, so Manchester United finished 6th, and they had a really unexciting year. They had been much better than that in the previous years. So that year they had lots and lots of tied games, and so their point total at the end of the season wasn't that great. Their offense was really down compared to what they were doing, how good they were before. And one of the things was Rooney had a really off year. And so that year he only scored 5 goals in 20 games playing during the season for Manchester United. And so that was way below his average for previous years, which was almost half a goal per game up to that point. And so the question that you could ask is, well, what if Rooney had scored goals according to his usual scoring pattern, or if he at his usual rate? So if he did that, you can see he would have scored about 12.5 goals in his 25 games roughly, which is an increase of about 7.5 goals over the whole season. So we can go back and say, well, let's tweak the parameters of the model. So now we've estimated all the models for all the teams. I have all the alphas and all the betas for all the teams. Let's increase Manchester United's offense to account for this extra scoring by Rooney, which we can do by just tweaking all the parameters. And once we have that, we can actually simulate seasons to see the outcome of doing this, or the impact of an increased scoring for Manchester United. So what would that have done? Would they have done better than their 6th place? Obviously, most likely that's what we expect, but how much better is the question. So if you do this, here, let me go back to full screen. Okay. So if you do this, you can see you can see that actually they would have ended, according to the simulation, they could have ended in 4th place, or they're the 4th best team now instead of the 6th best team. So now I did this, I do want to, go back to this here. Okay, so this column here is without doing anything and using Wayne Rooney's original performance, so the parameter estimated from the raw data. You can see something here. You can see that, so what I did is I estimated the model, and then I simulated 10,000 new seasons based on the model parameters. And then I report the average rank through the simulation for each team. And so here you can see that over 10,000 seasons, Chelsea, their average rank is 2.4. And Tottenham is the best for the team, for the league at 1.6. Well, that's in line with what I was saying earlier. These models, they tend to overemphasize a little bit the goal differences. And so Tottenham comes out as the best team here in terms of when you fit the model. Chelsea comes out as the second best team. Now you can see that Manchester, their average simulated rank is 5.29. That's actually the sixth best average rank. And so after the updating of the parameters, if you do the same thing, simulate 10,000 seasons, you can see that now for Manchester United, they just are slightly better than Liverpool and Arsenal and end up being the team with the fourth best average rank through the simulation, suggesting, of course, no more than that, but suggesting that, you know, if Rooney had done as he normally did, you could expect that they would have done better. And now that we say that, you can see that that fourth spot is really tight between Liverpool, Arsenal, and Manchester here, right? Okay. So now, going back to this independent Poisson. So these are the things you can do with this kind of model, which makes it interesting. So this kind of model is super simple, interpretable, and flexible. That is, you can actually easily add things. You can add an effect for red cards, which is something I talked about before, and see, for instance, what effect that has on the game, right? On goals being scored. And then you can add an effect for substitutions or for traveling, as we were saying earlier, or for other things. And so these are things you can do to try and see if try and catch any interesting tendencies here overall over the league. However, on the downside, I guess, this model tends to overestimate the importance of goal differences, as I said before. So if your goal is really on predicting the end result of the game, then probably you want to move them to an outcome-based model to avoid this kind of thing. Now, it also ignores the dependence between the scores, which is an obvious problem. There are fixes for that. There are other families of models that people have suggested, like the bivariate Poisson model or using copula models, which are interesting and definitely feasible. They make the inference more difficult, but they also work. And the model also struggles to capture ties. So this model is known to struggle with the probability for ties tends to be too low when you actually look at the implied probability based on the parameters. And so here, there are models that are built just to handle this problem. Diagonally inflated Poisson models is what they call them. So to give you an idea of what's going on here, this is the fitted value, the fitted table for standings at the end of the season based on the model parameters. And you can see what's in red there are all the bad fits, so to speak. And if you look at those bad fits, you'll see that really in every row when there's a bad fit, there's always something around the ties that are not caught properly. Okay. So
Alex, can I just stop you there for a sec? We have a question from
Okay.
Ryan Brody. He asks, can we weight the importance of offense and defense?
I wouldn't know upfront how to do that, but I'm sure you can come up with some kind of a scheme. It's possible to weight games, for instance. And so I think there are some people that suggest, for instance, whenever you have a blowout, like a 6-1 blowout, probably this game you want to downweight it in your estimation. On purpose.
That was the direction I was thinking of going with that question, as well as I know, like in some sports, being better at offense or better at defense has more impact on at least.
Yes.
Your
So I think I wouldn't know how you would specifically upweight or downweight just one of them. I mean, we could think about it, and that may be possible. But definitely, the downweighting of games is one that I've seen, where blowouts imply this game was something different going on, and so people will do that. They will downweight blowouts, for instance. So that takes away a little bit of that emphasis of, if you win 6-1, that doesn't, like, that's a fluke. That doesn't imply that the team is, 6 times better than the other team or something. And those kinds of blowouts, they tend to cause problems for estimation. they are the ones that are responsible for the goal differences also in the standings at the end of the year. And
exactly.
so by downweighting the blowouts, that's one way to improve for sure. Yeah.
Awesome.
Yeah. Thanks for the question. That's actually something interesting to consider as well, for sure. Okay, so here's, I guess, what we were thinking, looking at all of this is, it's possible to set these games up as homogeneous Poisson processes. So without going into the full details, you can define x of t as the number of goals up to time t. And if you do that, and if you use a constant scoring rate, like my theta h sub h was the expected number of goals for the home team, and theta a was the expected number of goals for the away team over the whole game. If you make those x and y as full stochastic processes where you actually keep track of the actual score and when goals are scored, not just how many, but when they were scored, then you kind of generalize the model to a homogeneous Poisson process. But the fitting of these parameters really goes back to the model, to the independent Poisson model. And in the end, you really only use the number of goals done over the whole game. And so this does require an extra assumption here, I guess, if you're looking at this model, is the assumption is that the scoring rate is constant throughout the whole game, which doesn't make sense probably in so many ways, right? So if you look at, for instance, these are just histograms of when goals were scored, you can see that there's kind of like an increasing trend a little bit, plus those two bumps around halftime and around the extra time at the end of the game. Really, those two bumps have to do with extra time, right? And so if you kind of fix your histogram to single out the extra time, you can see that the bumps are not as high, except perhaps for the extra time at the end of the game, which of course a team that's trailing will be going full out to try and equalize the game. So that kind of makes sense, I guess. So this is what we had in mind actually with all of this. How do we go into these like extra time and look at scoring patterns, for instance? So one way to go is to just generalize the model a little bit more and bring in time varying rates. And so use what we call non-homogeneous Poisson processes. So I don't want to go into the details here. That's not the goal, but let me just say that the key here is this bit here, right? So now what we are saying is that the scoring rate throughout the game will vary. The thetas still represent the expected number of goals over the whole game, but lambda now is a scoring pattern. And so lambda here will be high when in a region of the game or at the point of the game where you'd expect goals to be scored, and low otherwise, right? And so this lambda will be a function from 0 to 1, and the goal is to use it to describe scoring patterns. Now, of course, right now I've got the same lambda for the home and the away team. But you don't have to do that. You could have lambdas different for home and away. You could even have team-specific lambdas, league-specific lambdas. I mean, that's all up to the user, right? And so here what you do, and that's the generalization that we are looking at here, and Robyn will talk about, is we're still assuming independence for now. Obviously, the goal in the long run is to bring in an interesting and intuitive dependence structure between the home and the away goals. The thetas keep their original interpretation, expected number of goals over the home game, and so they're estimated exactly the same way as before using a GLM. But the key thing now is this lambda of t is this goal scoring pattern. And so to make sure that this all makes sense, lambda of t needs to be non-negative, and it needs to integrate to 1 over the range of the whole game. So here we renormalize time for the game between 0 and 1. 0 is the start of the game, 1's the end of the game. And so this lambda becomes kind of like a density, even though it's not really a density because the data you get are not independent observations from, like in the density estimation context, it's a little bit different because you get full goal scoring patterns for games. But the goal then is to estimate this lambda non-parametrically. And so that's where Robyn is going to come in and show you guys what she did and how she estimated these rates and what she did in some specific cases to try and make sense of all of this and see like interesting things from the data that she gathered. So I'm going to stop here.
Someone can ask a question to Alex while I get set up, I guess.
Okay.
But I think you need to stop screen sharing.
Yes.
Oh. Okay. Can I ask a question?
Yep.
Oliver Schulte. Yeah, thanks. Very nice presentation of the Poisson model. So I just want to see how this relates to Tim Schwartz's talk on in-game win probabilities. It looks to me like you were both aiming for something, a function that maps a time to, well, in Tim's case, it's a win rate. In your case, it's the scoring rate.
Yes.
Okay. So Tim used functional data analysis, and I think another difference is that in Tim's model, he can include covariates. So he can include information about what has actually happened in the game, other than just what is the current game time. Am I right? Is that the two main differences, or yeah?
Yeah, so here with this model, once you have your estimates of your functions, you can calculate winning probabilities, of course, because they are outcomes with the remaining time. But what these wouldn't do, and so in terms of using those as in-game evolving probabilities, they evolve over time, but they're not context specific right now. So that's the next step, I guess. So here, the analysis in some sense is marginal, right, over all the patterns that you see with all the teams. So the goal is to kind of come up with some idea of what's actually going on overall. But definitely here, what you could do is you could have, you could set up your rate so that it actually is context dependent, right? And so it depends on current score or score difference or something like this. And so then, of course, it makes the inference a lot more difficult, but it's still possible to do it. So that's where this would go, I guess, in the long run. Yes. But we're not there yet. And that is what Tim was looking at.
Okay, thanks.
Yep.
All right, I'll get started then. Okay, everyone can see my screen, I hope. So I'm going to talk a bit about the motivation of what I've been working on. So we look to use goal times and the non-parametric estimated scoring rate to analyze different aspects of the soccer game. So we can compare scoring intensities between teams, leagues, and or seasons. We can determine whether scoring patterns differ between home and away games. So we know already from the home field advantage that was in the expected number of goals that there is an advantage for playing at home, but we want to know, do teams approach the game differently? Do they play different on the road or at home? How does that look? And we can study the scoring patterns throughout extra time. So if we zoom in on those last few minutes of extra time, what might we find? And then we can expand to examine the patterns of other events, such as red cards, substitutions, player-specific scoring patterns, and much more. Oh, I need to click on something. All right. So a bit about our data. So we collect data from 4 of the top European soccer leagues. We have a focus on the English Premier League, and then we add data from Bundesliga, La Liga, and Serie A when more data is required to do an analysis. And we have 5 seasons of soccer available between 2014 to 2019 for each of these 4 leagues. And then times have been obtained through web scraping, flashscores.ca. So this website's really nice because it's very consistent from league to league, from game to game. It provides the data in the same format and it's very easy to use. And it also gives us, for these 5 years, to the second times for events, which is very key to get a continuous distribution going. And then we can collect information on the times and types of events, as well as those comments associated with each of those events. And then we can go through the commentary, find different patterns, find the player who scored, the team who scored, and all kinds of information through analyzing the text that's within it. So on the left here, we see what a typical game page would look like for one of the games. When you hover over different things, it tells you like the exact time an event happened. And then what we do is we web scrape it using Phantom.js, a headless browser, to get the source code, which we see on the right. So if you look at the gray line that's kind of highlighted, we see 90 minutes plus 7 minutes and 1 second, which on the game page will show up as 90 minutes plus 8 minutes of overtime. All soccer times are rounded up to the nearest or to the highest minute. So what we want is those exact times, those 7 minute and 1 second time, so that we can get as specific information as we can. And then we also get the icon that's associated with it and the comment associated with it. And then it's a matter of using the R curl and XML packages in R. Then it's possible to extract the information from the source code of the web page for each game. Then it's a matter of going through using the appropriate statements and functions to gather those important details that we want to further analyze. So some common issues that we have with event-based data, one for us in soccer is how to handle that extra time. So as Alex mentioned before, we often has it as 45 plus, 90 plus. So what we want to do is bring all those games onto a scale that matches for each game. So often we would have 45 plus 2 minutes. You would think of that as maybe the 47th minute of the game, but then there's a 46th minute that occurs in the second half, which happened after the 47th minute of the first half. So we need to find a way to make that uniform for everyone. So what we do is we take the start of the game as 0, the end of the additional time after 45 minutes as 0.5, the start of the second half as 0.5, and then the end of all the additional time as 1. And that brings us onto a continuous scale for every single game, which we can combine to analyze. And then we also have the problem where sometimes data appears outside of the game. So sometimes yellow cards, red cards are awarded way after game time. Here we see it's awarded 230 minutes after the game has ended. That's going to cause an issue when I rescale my data to be between 0 and 1. Sometimes I have goals that appeared before the game even started. So I need to make code in order to find those discrepancies and then do research to figure out what actually happened, where does that goal actually go in the game, or should it be there at all. Sometimes I have missing data where the goals that are labeled in the commentary don't match the end result of the game, so I need to do research to figure out what actually happened. And then VAR is a fairly new issue that I had to deal with. In 2018, 2019, it started appearing in some seasons where on flash scores, they would show, a goal would happen, and then a VAR would be called, and sometimes that goal could be removed. So I have to be able to look at the comments and figure out what actually happened to that goal if VAR was announced, and code in order to account for that. So now that we have our data, we can use it to create a scoring pattern. So what do we want? We want a scoring pattern with good soccer-like behavior, specifically around the boundaries. So we want our game to be confined between 0 and 1s because goals can't occur out of game time. At least we know that. And we also want it to be continuous to allow for different probabilities to be calculated. Sorry, I got a chat. Oh, press, thank you. And then, we want it continuous to allow for different probabilities to be calculated, and we also want it to be estimated non-parametrically to allow for the scoring pattern to vary from team to team or season to season, whatever we would choose. Oh, too far. Sorry. All right, so our first option, I won't go too far into it to save a little bit of time. Very popular non-parametric estimator is the kernel density estimator, where it kind of acts as a weight at each goal or each point of interest. And we're going to use a Gaussian estimator with a bandwidth omega, which we show here. A little bit of how it would look. The Gaussian kernel estimator for 10 goals scored over 4 games would look like this. So each X would indicate where a goal happened. We put a Gaussian bump over each goal, and then we add up the weight of those to create that estimator. So there's some issues that are very common with the kernel estimator, and there's definitely fixes out there that people can use. One issue is that when data is skewed, because the bandwidth is fixed for every single kernel, the outliers tend to get more weight and take weight away from the main portion of the data, thus underestimating the bulk of the data. The issue we have with soccer, and specifically, is that area spills outside of 0, 1. Because the symmetric kernels, we can get area going outside of 0, outside of 1, which is unrealistic for a soccer game, therefore not ideal for what we want to do. Our second option, which is the one we go with, is the Bernstein estimator, which uses nth order polynomial approximations that vary as they approach the boundary. So instead of having something symmetric, it's going to change as we move from 0 to 1. And so what this is basically, it's a mixture of beta distributions with data-driven weights, where we use the normalized sample cumulative intensity function within that. And what is that? Well, the normalized sample cumulative intensity function corresponds to the average number of goals scored over all games before time t, and gives an idea of how the momentum accumulates over the course of a typical game. So this is a little bit of what it would look like. So we have data-driven weights with beta distributions. So everything kind of adds up to a nice curve of what we would kind of expect, a little better behaved than the kernel estimator. So the Bernstein estimator provides a continuous and differentiable estimator that is free of boundary bias and is in fact has uniform bias over the unit interval. So moving forward, we're going to use this method of estimating the scoring pattern, which we combine with the expected number of goals to create an overall scoring rate for the game. So another little mathy slide. So we can determine the optimal order of the polynomial m by using cross-validation and what's known as the leave one out method, where here we would specifically leave one game out of a time instead of one goal out at a time. And then we can calculate that for a bunch of m. Here the lambda hat minus I refers to the scoring pattern estimate with the ith game removed. So this allows us to determine the optimal value to ensure the estimated scoring pattern is as close to that unknown scoring pattern using only the data to approximate it. And this is what we find. So we can create a league-wide season-specific scoring pattern for the EPL in 2015-16 and 2016-17. And so we put the Bernstein estimate over the histogram. So the Bernstein estimate is in blue on the right side over top of the histogram of that respective season, with the optimal m determined on the side. And then we have on the left the least squares cross-validation. So we select the optimal value of m by taking the minimum value of the least squares cross-validation. And then with so many goals in each of those seasons, it's not a surprise that the least squares cross-validation tends to plateau a little bit, but we're still able to calculate that optimal m. And so what do we see from these curves? Does this seem constant? To me, it seems like things are kind of increasing until halftime and then again increasing until the end of the game. So I definitely see an increasing pattern from start to finish, implying that maybe Lee's model that Alex talked about might be a little bit of an oversimplification and something else is going on here. We can also look at team-specific scoring patterns, where we look at all goals scored by the respective team in the combined seasons between 2014 and 2019, so that we can get enough data to actually look at. So we look at Chelsea, Crystal Palace, Manchester City, Manchester United, and we have their least squares cross-validation graphs for each of them to determine the optimal order of the polynomial for their Bernstein estimates. And again, a constant scoring pattern seems a little bit of an oversimplification to me. There's definitely some type of increasing trend going on here, which we want to further look into. Then with the expected number of goals and the scoring pattern, this information can be used to determine that given a goal has happened, what is the probability that that home team scored the goal or that away team scored the goal. So I won't go too much into this, but we can figure out the probabilities that who scored the goal given we know a goal happened at time t. And then we can use the scoring patterns to take a closer look at how teams perform at home or on the road. So if I look at Manchester City and Manchester United, their home performances and their away performances, what I want to know is, do these really differ? Well, we can see that they definitely differ, but is that a significant enough difference to say conclusively that that is true? What we can do is we can conduct a permutation test. So we test whether the home and away scoring patterns differ by shuffling all the home games with all the away games, re-optimizing those home and away games to create new Bernstein polynomials, find the difference between those two scoring patterns, and that's what our test statistic is. It's the gray area between the home and away estimated scoring patterns. So that's in the bottom left, where the home scoring pattern is in blue and the away scoring pattern is in red. So the area between is our test statistic. We do this many, many times in order to get the test statistic for every single permutation. And then what we see is the result on the bottom right. So from the test, we find an achieved significance level of 0.14. Therefore, we do not have enough evidence to say that the home and away scoring patterns do in fact differ for Chelsea, which we see here. All right, so what about extra time? Can we take a closer look? So I want you to imagine these scenarios. The game is tied. The referee announces 4 minutes of additional time. How do these last moments play out when you know what's at stake? Do you push for that extra goal to secure the game, or do you wait until the final moments before risking that loss? Maybe your team is ahead by 1 goal with 2 additional times added to the game. Do you hang back and play defensively? Does the other team take chances in order to get that equalizing goal? Do they maybe make mistakes that they wouldn't normally take trying to get that extra goal? What can we expect from extra time given those different scenarios that can occur that might influence how those last moments play out? So can we assume the scoring pattern is the same when you're ahead or behind going into added time after 45 minutes or after 90 minutes of play? So this is a little bit of just a tree diagram to see the different scenarios that can happen after 90 minutes of play. So after 90 minutes of play, what we do is we combine all 4 leagues, all 5 seasons, because there aren't very many extra time goals and we want to get as much data as we can. So we combine absolutely everything. We get a total of 7,230 goals from all the combined data. And then of that, we get 1,347 goals, which had at the 90-minute mark, 5 minutes or more were announced as extra time. Of those games, 788 of them had a goal of 1 difference at the start of extra time. So once that 90-minute mark, you know there's 5 minutes or more going to happen. You have a 1 goal difference. What happens? Well, the ahead team scored 93 of those games, and the behind team scored 98 of those games. And we want to compare those goals in order to see maybe how did that ahead team approach the game, those extra 5+ minutes when they knew they were ahead by 1 goal. How did the behind team approach those extra 5+ minutes when they knew they were behind by 1 goal? So that's what we do. We do, again, a permutation test to determine, are these really different? So first we look at the difference of 1 goal. So at that 45-minute mark, there are 0 to 3 minutes of added time with a 1 goal difference. The team that is ahead has a scoring pattern that looks like this on the left. The team that's behind has this next scoring pattern, and do these really differ? So we take the area between, run a permutation test, and we find that there is not enough evidence that these scoring patterns actually differ. The more interesting one is if there's a difference of 1 minute, there's 5+ minutes, difference of 1 goal, 5+ minutes of added time after those 90 minutes. So the 90-minute mark, they announce 5+ minutes. You know there's a goal difference of 1. The team that's ahead has a scoring pattern, as we see on the bottom left. The team that's behind has the next one. And then the test statistic is the area between the 2 curves. What we find is an achieved significance level of 0.1, which gives us evidence that those scoring patterns may actually be different. And why might that be? So what's actually going on? What I would think, maybe you would have your own opinion, is perhaps the behind team is really getting desperate in those very last moments of the game around the 80% mark. And they're maybe making silly mistakes that the other team is able to take advantage of and really scoring a lot of goals in those final moments of extra time. Like maybe they just give up. So it's a lot of interesting stuff that can happen there. And then what we can do is we can adapt this model into other areas of the game, like individual players, substitutions, red cards, conceded goals, and so much more. So here I have the scoring pattern for Lionel Messi, which to me is quite surprising. I think of Lionel Messi as a pretty consistent goal scorer. Maybe someone else has a better idea of how he plays the game, but to see him really have a spike at the end of the game, maybe he's only put in, and we need to consider when a player even starts their game, if they're a sub or something. But we can see the different things like this and kind of get an idea of how he plays and maybe how to be defensive against him. And then we could also model home team substitutions as well as away team substitutions, but you see definitely a large spike at halftime and most of the substitutions happening at the end of the game, which is definitely what we would expect. So the possibilities are endless. We can use this for different sports, different fields, and do all kinds of things. So that's our talk. Thank you for listening. I kind of rushed through that to try to save time.
Well, great stuff. Thanks for the clear talk. So maybe I'll just get you to stop sharing your screen.
Sure.
And I'll just go to the gallery view here. And so if anyone has questions, you can either put them in the chat box or just come online here and ask away.
Hey, Ryan here again. I'm interested in those trends that show essentially more things happening towards the end of the game, and if something like fatigue and fitness had been considered as a possibility there, and that some teams just have higher levels of fitness and they're going to likely score more goals as the teams they play against, weaker teams potentially, start to fall off and make more mistakes. And if this kind of concept of just how fitness might differ between really strong teams and weaker teams, or teams with higher depth, like more subs, better subs, that kind of thing.
Yeah, it's definitely something to consider. It's a little difficult to do with our free data we get online. Ideally, like you can see if you had like XY coordinates, you can see how much players are running, and then by how much movement they have, you can really quantify that fatigue element of what's going on. With better data, I would hope we could get into that.
So in general, the assessment of why is fairly challenging, I guess. With like you just have the events, and to understand any of them, you'd have to dig back in and try to figure out what the events leading up to that give rise to the observed patterns.
Yeah, so all we have available is like the commentary you would hear the announcer say during the game, right? So it's hard for us to quantify how fatigue would come out from that kind of data. We would definitely need more data, but we could consider things like substitutions and see maybe when a sub come in, does that add an extra layer of like offense to their game, or defense if it's someone else.
Mm-hmm. There's a question from Jody Hawley. What other sports do you see this applying to? I wonder specifically about combat sports and whether there are issues readily apparent for that type of event.
So it can definitely be applied to like sports like hockey. So basically anything that's on a fixed time interval can be applied to this, where you have like a certain event, like a goal or something happening at a very given time. I'm not too sure about like combat sports. I don't know, maybe Alex, you would know about combat.
I guess if you think of, judo or karate, where the guys are fighting until an event occurs and some number of points is scored, perhaps that would work. But I'm definitely not an expert enough to to guarantee anything. But that could work. That's, even though here you only have two people, it's still kind of the same principle. They're fighting it out until some number of points is scored. So what differs here, of course, is goals come one at a time, and you can't have 2 points for a goal. But there's a lot of work on basketball already where you have 1s and 2s and 3s. So I mean, clearly, you could probably do something there as well. It's a matter of getting good enough data, perhaps. One thing I would point out, going back to the previous question, for trying to understand fitness of the team and so on. Robyn mentioned subs. That's one thing. If you got somebody fresh at the end, like a striker at the end of the game, that may have an impact, obviously. I think some of the things I've seen are people trying to account as covariates for the amount of traveling, and that was done. Like if an East Coast team would play on the West Coast, for instance, try to factor that into the games. I think that has, from what I remember, that has mostly failed. Like it didn't come out as strongly. It's surprising. You'd expect it would make a big difference, but it doesn't necessarily come out. So that's not enough. But you could definitely have covariates, like if they had back-to-back games, or for European soccer, if you have the top teams are also playing UFA Cup or whatever other things. And so if they had a Wednesday game in another country and they had to, like, that kind of thing could be factored in, obviously, as covariates. I can't say that I remember having seen it, but if I'm thinking about it, probably I saw it somewhere. And so that might have been done. I remember that for traveling, what I saw was not very conclusive. But for European games elsewhere, I don't remember. Perhaps it was just suggested, but that's something that could be done. But that's not the same as in-game fatigue, for which you need more data than what we have now.
Okay. So I have a possibly terribly ignorant question, but you're showing a lot of histograms. Like, how do you discretize the data, and like on what scale, and how do you, and like, could that affect anything, or is it just how you've been presenting it?
I just give the histogram as like a background so you can see kind of how well ours is fitting. The histogram is just like a very visual thing that a lot of people can relate to. Ideally, I would just remove it, but then you'd have to take my word that it is a good fit.
Right, okay.
And then I guess like the number of bins and stuff will change how it looks, right? So the more bins I have, we want to find that balance between bias and everything of the histogram, fitting the data too well or not fitting it enough.
Right, okay. So really, it doesn't, like, nothing depends on that. That's just the way you visualized it.
Yeah.
Okay.
We've just picked the number of bins for the histogram to look good, right?
Yeah.
I mean,
yeah, fair enough.
That's the idea of the automatic fitting of the non-parametric curves, is to avoid this discreteness of bins altogether.
Right.
Yeah.
Good point. Okay, Tim Swartz, did you have a question?
Sure. Hi, Robyn and Alex. I really enjoyed that talk. I have just a few comments. So I really liked the Rooney analysis, and I was thinking that you could use that in terms of player acquisition. Like, for example, Real Madrid is always talking about getting Mbappe on their team. So you could kind of determine how the acquisition of Mbappe would help Real Madrid. And then a couple of other comments. As I'm sort of a casual gambler, and I can tell you for sure that the lambda function, it depends on the score differential, and Robyn sort of pointed that out at in those last couple slides. And I was also thinking, other people have tried this a bit, but those strengths, the offensive strengths and the defensive strengths, those have to be dynamic. There's red cards, key players are in and out for a game. There's teams that are traveling and are tired. I don't think a team's strength is constant throughout the year. Okay, yeah, again, thank you very much. That was a great talk.
Yeah, for sure. There's so many different things that we could add. For me, it was only 5 years of the exact times were available on flash scores. So the more data I could add, the more I could go into those different elements of what could be added at specific times. But I was a little limited with what I had available for me.
One thing I would add, I agree obviously with your comments, Tim. So that's how, so for the work I presented at Van Sash a few years ago, that's how I incorporated red cards as another covariate, which is a flag, which is on or off for if a team is a player down or not. And by doing this, you're just augmenting these scoring rates by adding another component for, being down a man, and you can estimate the impact of that. So now the question becomes, it's always having enough data, right? But you could definitely have something that's turned on when the goal difference is 1, and something that's turned on when the goal difference is more than 1, let's say. And so you can add more of those. So whether or not you can estimate those parameters well, of course, becomes difficult, especially if you want to keep this non-parametric rate function there. But I guess, this is where this should go, right? To really make it fully dynamic. Then, because, this, I guess our idea with the time dependence is an overall pattern of what's going on. And I think I like definitely myself Robyn's analysis for the extra time, because, extra time is constrained. It's very short, and you go in and this game situation is not going to have the time to change that much usually because it's short. So then that kind of makes sense there. definitely when you look at these estimates. But of course, over different games with different situations, with red cards or not, and so on, that makes it a little bit more tricky. Now, still, those models, they fit the data reasonably well, which is quite surprising. But as a gambler, you would want something dynamic. I can see why.
Excellent. Okay, so Ryan, do you want to ask your question now?
Oh, sure. Yeah, I was wondering, just to increase the number of events you can test on, if you might try replacing goals with a combination of shots and some kind of scoring rate metric.
Yeah, that could definitely be something to look into. That would, for me, would involve a lot of like text analysis for all the different ways you can say someone took a shot on net or someone took a shot and just missed, and analyzing, okay, well, how close was that actually just by the words that they say?
Yeah.
So for me, it's just easy. It's like an icon and then confirm that the comment is talking about a goal. But yeah, it would definitely go into more detail. I'd have to see how good like the way that they talk about shots is in order to see if I can actually get that data clearly from the comments.
The other option is to make good friends that can provide that.
Yes.
Because they already
if anyone
have
has good data.
like Sports Logic or these other guys.
Yeah.
It's definitely a way it could go in the future for sure.
Excellent. Lucas, please go ahead.
Sure. Hi, Alex. That's a great talk. I have a question. So I'm just wondering, how would this model differ if, instead of using the goal scoring rate, and then we use something like the sum of expected goals? So would that, change the model a lot?
I'm sorry, can you repeat your question?
Sure. So I was just wondering, so this model is using like the goal scoring rate, right? I was just wondering, how would this model differ if using something like the sum of the expected goals, which is kind of a popular metric that used in soccer analytics, right? So basically, you can get the expected goal for each shot, and then you sum that up over the entire match, and then use that as the response.
Okay, so kind of building on what Ryan just talked about with the shots that could happen, how much the probability of success that is if you could find out how many shots were given in a game.
Right, yeah.
Yeah.
I'm not sure. So the issue with anything that's Poisson type process is the more you go into breaking it down into a sum of the small things, it's less clear that the model applies. It's a good, surprisingly good marginal model, so to speak, when you just zoom out and look at game level stuff. As soon as you go in, it becomes a little bit more tricky. So expected value or expected goal metrics, that's what they're not going to be constructed based on something like this, at least to my understanding. They do break it down into the sum of all the little tiny things that should lead to you winning, which is what's so great about what they do, for sure. This is on our radar, things that we need to look into for sure. I mean, this is where I think soccer analytics are going, definitely. The problem, of course, with that is the more in depth you go, the least, mathematically anyways, the least intuitive this can all be. It becomes difficult models to look, to understand and assess for goodness of fit, for instance. But definitely, I think they are important tools, these things. So here, I'm not sure if I really answer your question. I hope I do. But I don't know that it would be applicable exactly this way. Now, for some of those expected goal metrics, you do have stochastic processes in the background. And so there's a link, but it would be different. Because here, anything that's Poisson is a counting process. And it's a very simple counting process on goals here. So, I mean, as soon as you want to do other things, if you want to improve your outcome prediction, definitely you actually forget about modeling goals. You go straight to modeling outcomes and you can improve.
Okay, yeah, great, thanks.
Okay, thanks for the question.
Okay, great. Thanks everyone for all your questions. I think this is a good point to stop the recording, so I'm going to do that now. But just before I do, I want to thank Dr. Leblanc and Robyn again for a great presentation. And yeah, thanks very much.